Good morning. I'm presenting the scale model tests of a moored tanker at Leixões port with the breakwaters extension. This is a work that has been done in the National Civil Engineering Laboratory in Lisbon with the collaboration of the Polytechnic Institute of Lisbon and the Technical University of Lisbon. So the objective of this work is to assess the impact of the increasing the length of the north breakwater by 300 meters. The port of Leixões is located in the northwest of Portugal, near Porto city. So the port is looking to extend this breakwater by 300 meters. And one of the commissions they ask for our laboratory is to do physical model tests to assess the impact of this. So the wave conditions inside the port are to be measured, and additionally to this we will monitor the behavior of a moored ship in post A. So the results of these physical model tests will be used to validate the numerical models for moored ships inside ports. So this is our experimental setup. We have the port structures depicted at a 1:80 scale. Located inside a tank of 22 by 23 meters. This is the breakwaters extension, and here we have the wave generator with a 6-meter length wave pattern. For this physical experiment we used a ship's model. It's a tanker model of a tanker named SO Osaka. It's a 1:100 scale model. It has 3 and 45 centimeters of length, about 54 centimeters of draught and 23 centimeters of draft. The model weighed a total of 214 kilograms. For this moored ship model, we used several types of measuring equipments. Amongst them we have a video camera to record all the tests. We have 8 wave gauges to record the wave surface elevation. Some of these gauges are set up in arrays, so we can also infer the wave direction from this data. We also have, in the same position of these wave gauges arrays, we have ADVs to measure velocities. Then we have the mooring system with a system of cables that I will explain a bit afterwards. And we have load cells that will measure the forces in the mooring system. Then we have a set of 4 video cameras that are part of our motion capture system. So our wave surface elevation is measured with resistive probes. We have 8 in total. 6 of these probes are arranged in 3 gauges arrays, 1 in front of the ship and 1 on the side of the ship. We also have, in the same locations, ADVs to measure velocities. Our motion capture system is an OptiTrack system. It's made up of 4 video cameras, a set of targets placed on the deck of the ship, an acquisition system, and this system records all the data with 50 Hz. To measure the forces in the mooring system, we have force sensors. They are tension, compression, load cells, and they can weight until more or less 6 kilograms. So the mooring line system is made up of the force sensor that I showed before, a rigid cable line that attaches to the ship through a pulley, and then we have a calibrated spring that will simulate the force elongation of the cable that we want to represent. This force elongation calibration is made up with a contraption that is a flexible stainless steel sheet that bends and with a system of calibrated screws, the traction on this sheet will give us the force elongation that we want to represent. For the fender system, it's the same methodology. We have the force sensor, we have the rigid cable line attached to the same calibrated spring, and then through the use of a lever we can convert the compression force into a traction force. So here's a close-up of the system. So we have the spring system is the same setup as for the mooring lines, and the lever system just converts the compression force for the fenders into a traction into the line. Before all tests, we have to make a series of calibrations. We have to calibrate the mass distribution in the ship, so the center of gravity is where it's supposed to be. Then we have to make decay and tilt tests to make sure that the inertias of the ship are correct. Then we need to calibrate the wave gauges and also calibrate the camera system. After all this, we are ready to do the experimental tests. For this series of tests that I'm presenting, we made 9 different tests with different peak periods and different wave heights in the prototype. All the tests were repeated once, and the tests 4, 5, 6, and 9 were repeated 10 times. So this led to a total of 48 tests. And this is a video of one of the tests. You can see the ship moving, you can see the waves diffracting around the breakwater, you can see the camera system, and you can see the mooring line being extended as the ship moves. So the wave measurements that we make give us many data. So we have time series for all the data that is acquired, and all this data is synchronous, and then we can make the analysis. So here we can see the wave gauge elevation at the wave maker and also at the ship starboard. From this time series we can get frequency spectrums and get the spectral parameters of the waves. From the wave gauge arrays and from the ADVs, we are able to extract the directional spectrum of the waves. From the camera system, we get the linear motions of the ship and also the rotational motions of the ship, and then we can analyze this data. The mooring forces also are registered and then analyzed. Here's an example of a time series of the mooring forces, and from this we can get all kinds of parameters. In terms of repeatability analysis, the test number 9 was repeated 10 times, as I said, and we can see here that the significant wave height measured in the probes for the repetition of the test is quite good. The maximum error that we have is around 8% for the wave height. For the peak periods, we have slightly bigger errors, around 7% at the wave maker and 20% at the side of the ship. For the motions, the rotational motions, for instance, we can see that the test repeatability is quite good. And for the motions, also it's a very good agreement. Looking at the statistics, for the motions, we have error percentages of around 16 and 18% for linear and rotational movements. And finally, for the forces measured on the mooring system, we can see that for the average forces and the significant forces, the repetitions are quite good. The only biggest error occurs for the maximum force, which is expected. So we can see that for the significant forces on the mooring lines, we have a maximum error of 10%, and for the fenders of 15%. So with this work, we show that the measurements of the OptiTrack system proved to be very efficient for characterizing linear and rotational motions. The calibration of the mooring stiffness was able to reproduce the desired curves, and the test repeatability analysis showed very good statistics. We still have to investigate the effect of the pre-tensioning of the moorings in the response of the moored vessel. I would like to acknowledge the funding from FCT and from the Institute of Engineering of Lisbon. Thank you very much for your attention.